Okay, Claudia, let me answer your first question. I decided to make a video for this. Um, One of the things you can look at are the first few homework problems. Um, but let me answer it in general because it's a really good question. Um, if the population distribution, so we're going to call this let's call this the population distribution, or PD for short. If it's approximately normal, if population distribution approximately normal, then n has no lower limit. All it has to do is be greater than or equal to 1. A sample size of 1 would simply have a sampling distribution of mu comma sigma over the square root of 1, or mu comma sigma. But a sample size of 2 or 3 or 4 would be okay with, this is only with, you understand, with quantitative data. And I'm sure that's what you're asking for. I get the sense of that in your question. Okay. Now, I know that's not what you're asking, but as the population gets more skewed, more non-normal, so as population distribution gets less normal, then n must increase. And as you say, it's common sense that comes into play, but there is a cutoff point, and in general, if n is greater than or equal to 40, then n yields an approximately normal sampling distribution. Here, let's use SD for sampling distribution of mu comma sigma over the square root of n. Less than 40, and then the issue is in doubt. Okay, now in number 2, question 2, so you have the, let me just put this in here, let me copy this. Put it in here. Paste this in. Make this a little bigger. Okay. All right, you ask a whole lot of different questions in here. So the first question, I'm confused where you get this information from. Well, 90, 95, 98, 99 are simply commonly used confidence intervals. Now let's talk about what exactly is a confidence interval. As I said in my the PDF I sent you, the confidence interval equals the sample statistic plus or minus a certain number of z-scores, that is a certain number of standard deviations to the right and to the left, plus minus, times what's called the standard error, which is simply a standard deviation based on p hat. Now, why a confidence interval? Because in the original model, where the previously known p was stated as the center, p hat was 2 or more standard deviations away. P hat, the z-score of p hat, was greater than or equal to plus or minus 2. Therefore, P is rejected. Why? Because we consider P hat to be representative. It's a sample that's not too big, not too small, random and independent. So if the previously known P is far away from P hat, then we think that P is unlikely, and that therefore we want to make an interval around P hat of plus a certain number of z-scores called z star, we haven't stated what that is, times a standard deviation based on p hat. And we want this interval to be as wide as possible. That is, we want it to cover as much of the area under the curve as possible without being physically too wide. So here's what I mean. So here's p hat. Okay, let's talk about an example. Okay, let's say we do a poll and we've rejected what p was, and the results of the poll are 53%. Okay, now we would like to be 95%. We would like to be 95% confident of what we think is the new popularity percentage. Okay, so p hat equals 53, and I don't know, let's say the standard deviation of p hat q hat over n, we'll just say for the sake of argument, is 1.5. Okay, now we want to be 95% confident, which means we're going to go 95% under the curve would be 50% on the right. I'm sorry, 56% on the right. P hat equals 0.53. So this would be 0.545, and this would be 0.6. And over here would be 0.515, and here would be 0.5. All right, now we've gone 2 standard deviations to the right, or let's say 1.96, which is what the book says. Now the video that we refer to says 2. Well, 2 and 1.96 in terms of how much area under the curve are very similar. Now let's just talk about that for a second. So let me get my calculator going here. If you actually do, here, let's do this. So let's do a second and vars, and we're going to do normal CDF. That is, we're going to measure the area under the curve from -2 standard deviations to +2. So what's that area? Okay, 0.9544. Now let's do the second, or about 95%, right? I mean, pretty close. So let's do second vars again. Normal CDF, 1.96, comma, I'm sorry, it should be -1.96. Comma, 1.96. Okay, and you can see that's exactly 95%. Now, if you use 2 or you use 1.96, it's going to be approximately the same. However, 1.96 is what's used in the book. It's what's available in your table, and it's what we're going to use in the course, and it's not a difficult number to remember. Anyway, so that's where that, if one thing says 2 and the other one says 1.96, well, they're effectively saying the same in terms of how much area under the curve is covered by negative 2 comma 2 or negative 1.96 comma 1.96. So it's pretty easy to see in either case, 1.96 or negative 2 comma 1.96 or positive 2, you're going to get 95% under the curve. So what the level of confidence means, we are 95% confident that the true P, whatever the true popularity or whatever, the true proportion of people who are in favor of whatever, is between 0.5 and 0.56. So let's go back to your question here for a second. Okay. Now, how do you know which percentages to use? You're always told, if you are asked to compute a standard deviation, a confidence interval, then you're going to be told what percentage to use. Now, the confidence interval can be anything. It could be 0, it could be 100%, and anything in between. But commonly, confidence intervals are only computed, or not only, but, like in terms of our book or whatever, 90, 95, 98, and 99. Now, if you look here, I might as well deal with this question that you asked before, and let's look at a table that's very much like the one you asked about. I'll go to AP Statistics Exams, and so let's look at, okay, now, so we go to the end of the test because it's where the tables are. Now, here's z-score probabilities, another z-score probabilities, and now here is the t-score table. Let me make this bigger. Now, you'll learn, we're going to do stuff with the t-score table later on, but for now, here's the only thing you need to worry about is the bottom row where it lists confidence level. So here's 95%. And above it is the z-score that goes with it, 1.96. Okay, so you'll always have this available to you. Now you can use the calculator to find these, but it's kind of a pain in the neck. But I'll show you how to do that if you're interested. So here's 95%, and here's 90%, 1.645. Here's 80%, 1.282. So here's 98, 2.326, 99, 2.576, and so on. 99.5, 99.8, 99.9. As the number of standard deviations that you go to the right and to the left of p hat increases, then the level of confidence goes up. But as the number of standard deviations you go to the right and to the left of p hat increases, the bigger the interval is in which you think p might be. So in other words, your level of confidence is going up, but so is your uncertainty about where exactly is p. Why? Because the interval has gotten bigger. So this takes me into your third question, which is, I don't get why your confidence decreases as the margin of error decreases. Okay, so let's make a copy of this. These are all such great questions. All right, so let me put this in here. I'll paste this in. All right, now let's scroll down. Okay, let's show the question. I don't get why confidence decreases as the margin of error decreases. Well, yeah, what you're saying, isn't it a good thing when the margin of error decreases? Yes, but only if confidence doesn't decrease. Now, here in the curve I made above, okay, P could possibly be anywhere between 0.5 and 0.56 with a 95% level of confidence. We are 95% confident that true P is between 0.5 and 0.56. But the interval is so big that we do not know, it doesn't give us any confidence about who is actually ahead. Let's say this is a popularity poll about two political candidates. Why? Because the confidence interval includes 0.5. Now the confidence interval doesn't say it's more likely that it's in the middle and it's more likely that it's close to p hat. That is absolutely and totally not true. It just says we are 95% confident that it's somewhere in that interval. If that interval includes 50%, then it could just as likely be 50% as 56. And if it is 50%, then it's a dead heat. We don't know who is more ahead. So you only want to make the confidence interval smaller by increasing n, not by decreasing confidence. Okay? Now, your last sentence, you don't want to say you mean you are closer to the mean, so you have a better idea where there be less deviation. Yeah, okay, but you probably want to say less variation, but you have the right idea. Yeah, there's less variation, right, because you make the standard error smaller. Okay? As n increases, as n approaches, let's put it in the language of limits or whatever, as n approaches positive infinity, the standard error approaches 0. The bigger that n is, the smaller, because the standard error has an inverse relationship to n. It's p hat times q hat over n. Now notice, it increases to the square root of n. Okay? So you have a law of diminishing returns. As you want to get the standard error smaller and smaller, you have to get n has to grow geometrically in order to, or exponentially, I should say. N has to grow exponentially in order to get the standard error to decrease arithmetically. And so it can be costly. You've got to poll more people. So that's, you got a logistical problem. And so there's this trade-off in terms of getting the standard error smaller. But you don't want confidence to go down. You could make the standard error smaller by making z star smaller. Then you'd say, I'm 90% confident. And let's say you go 1.645. If you went 1.645, then you would definitely not include 0.5. But then you would only be 90% confident. There would be, you're only 90% confidence. You are unconfident about 10%. And that's, you may want, if a lot is at stake, 90% confidence may not be enough, which is why people spend so much money on polls. They spend millions and millions on them to gain some kind of certainty about what's going on. So, anyway, so this is another attempt to answer these questions for you. Please let me know if you find this helpful, either one of these things that I sent you. And any further questions you have, please don't hesitate to send them to me. and I'll try to get back to you on a timely basis. Tomorrow I'm going to be out of touch for a while. I'm going to be around all day today. Otherwise, I'll see you next week.